So I would like to preface today's workshop by saying that this is a very introductory workshop on what data analytics actually is. We won't be going into a whole lot of detail as to what kind of things you'll be coding up or a lot of the different concepts that come up in data analytics. There is a whole subject that the university offers called the elements of data processing. So if you're interested in something like this, feel free to take that subject. There's a whole lot of things you can do and learn. So if that is step one to learning what data analytics is, today's workshop can be interpreted as step 0. So we will be going into a larger overview as to what you can expect on what data analytics is, and it will be very brief in the sense that you won't be going into a whole lot of detail as to how to tackle it and what to do and so on and so forth. Before we start getting into the actual concepts for today's workshop, can I get a quick understanding of what people think or what people expect when they hear the words data analysis or data analytics? So what are some buzzwords, or what's like the first thing that pops into your head? Feel free to either put that in the chat or just say it out loud. Graphs, yes. Visualization is definitely a very big part of data analysis. Patterns and trends, yep. Big data. Insights, yep. What do you mean by that when you say insights? Predictions, yep. Great. So we have a fair idea. Yep. Derive actionable insights for business decision making, wrangling. Yeah, great. So we have kind of a good idea of what we want to do when it comes to data analysis. So if you have a quick Google search of data analysis itself, it will basically tell you that it is the process of collecting, modeling, and analyzing data to extract insights and support decision-making, which is exactly what one of our students said in the chat. Now that might seem like it's a lot of big words. You don't know how to exactly digest that. So the way that I like to think of data analysis is essentially it is turning raw data into useful information. Now, one of the very important things of data analysis is you need to be able to distinguish between the phrases data and information. When we speak in English, a lot of times we can use it as synonyms, but the way that I like to think of it is that they're two very different things. When it comes to data, it is essentially, you can think of it as just a bunch of numbers or words and classes that you can attribute to a record. It doesn't necessarily make a lot of sense if you just have a big like spreadsheet of, or like a survey, and you just give it to someone. You don't necessarily know what to do with it or what to make sense of it. Information is data that is useful, meaningful, and comprehensible. So it is something that you can understand and relate to other people who may not necessarily have an idea or have the background knowledge about the topic that you're investigating. So that is the two main distinctions between data and information. Now, we may ask, why do we do data analytics in the first place? It was kind of said in the definition itself. It is a way of making informed decisions with the foundation of data to either make or support your claim. So you might say something or have a hypothesis, but you need to be able to back it up. And that's where data analytics comes in. So when you do data analytics, no matter what kind of project it is, the way that I like to think is that there are 3 main steps of being able to analyze data in the first place. One is you need to have the data in the first place. So that will be your raw data. Second, you need to be able to figure out what kind of models you want to use, so modeling. And third is visualization. So at the end of the day, you want to be able to see what your data looks like and what it's doing. More often than not, you're going to have data sets with thousands of data points. And when that happens, you don't necessarily, of course, you're not going to be able to like understand what thousands of data points are doing at the same time. So you want to be able to know how they're behaving and what they're doing. Visualizing that data is what makes and helps you gauge what your data is doing, and it allows you to support your decision making further. So it's also a way for you to be able to make it make a layman understand better what your data is doing and how you are trying to investigate something and what kind of conclusion you make out of that. So it is particularly this ability to visualize data that makes data analytics so powerful, especially when you're using like a program like Python or R. Can we go to the next slide, please? Great. So when I say data versus information, we need to be able to turn data into information. So first, we need to understand the types of data that we can possibly be dealing with. So before we get to our data set, we need to understand the data we encounter. So there are two main types of data. You have qualitative data, and then you have quantitative data, as some of us may be familiar with. Qualitative data is when you're trying to describe something in terms of its characteristics. So it can be something as simple as saying that something is hot or cold, or a color, or even size when you're trying to describe it as it being big, medium, or small. When you're saying quantitative data, it is describing the amount of something or describing a characteristic in terms of numerics. So that can be the weight of something, it can be the size of something, when you are trying to say like the height or the dimensions, or it can be something such as price as well. Once you get this data, this can be further described as discrete and also continuous data. So discrete data is something that can be broken down further, that cannot be broken down further, sorry. So stuff like integers, so you can't exactly have 2.4 of a person. So if you're describing people or like the population, that can be thought of as a discrete form of data. Continuous, on the other hand, is something that has fractions or decimals. So 3.4 kilograms, let's say. So that will be continuous data. One thing I would like you guys to notice is that you have two kinds of things. You have numerics, which is your numbers, but you also have words to describe something. So that is a key point to note. Now that we have what we know we can expect from our data or from our potential data set, we need to have a think about what you can expect when you see a big data set, right? So in an ideal data set, you'll be having all your records filled out correctly and it's ready to use without you necessarily needing to directly edit or change the actual records or data points themselves. Now, I'd like you to notice that I use the word ideal data set. This is because it is very rare for you to find a data set where you don't need to be changing or doing any kind of data wrangling to it before you're able to actually use it. In a real world data set, on the other hand, it will contain all sorts of issues with the records, whether that be you have a certain missing value in a particular attribute or column, you have human error if you're doing something like filling out a survey and using that as a data set, you can have misspellings, missing decimal points, which will completely throw off if you're trying to do any kind of analysis. You can have formatting errors, especially when it comes to dates. Some people write it the American way, some people write it the European way, some people use slashes, dots, all sorts of things. So it is important to realize that real data sets won't always be clean and useful. So it is our jobs when we're doing any kind of analytics is to perform before we perform any kind of modeling or visualization, is to make sure that our real world data set can be sort of resembling an ideal data set as much as possible. And that's where data pre-processing comes in. And that's what is called data pre-processing. There are a whole bunch of different ways that you can do that. We're not entirely going to go into that today. But if you'd like to discuss that further, feel free to hang around later. I'm more than happy to take questions about that. If we go on to the next slide. Great. So now we have a workable data set. From here, we need to figure out what kind of models we want to use, or even what kind of modeling we want to do in the first place. There are many different kinds of models that you'll encounter. These are just some of the ones that I think are one of the bigger ones, or the ones that people use more often. So you have probabilistic modeling, you have clustering, regression, and time series. So probabilistic modeling deals with random variables and their distributions to a model in order to model a behavior or an event. So more often than not, there will be a lot of math involved in terms of the assumptions for the models or that you'd like to implement. Again, we're not going to be going into a whole lot of that today. But an example of a probabilistic model can be something like naive Bayes theorem, or the naive Bayes model, which you can use to predict the probability of a record being in a given class. When it comes to clustering, it involves grouping data points together. The closer a data point is to one another, the more similar they are. You'll find that some data sets create these groups of data points or clusters, which you can use to derive conclusions about their distribution, whether that be conclusions about distribution, about how similar data points are, or even decide if there is any clustering going on to begin with. A good example of a clustering model would be something like the Kmeans model, which if you give a certain point to the model that you're using, it will basically figure out which data point is closest to, and from that figure out which cluster it's in and classify it to that cluster. We also have something called regression modeling or regression analysis. It involves modeling the relationships between a dependent variable, which will be your classifier, with your independent features. So in terms of something like linear regression, it will be something along the lines of y equals to ax0 plus bx1, so on and so forth, plus c, where a, b is your coefficients, your x1 or x0, so on and so forth, will be your independent variables, and c will be a constant at the end. You can also think of nonlinear regression, where you'll be modeling a quadratic, cubic, quartic, so on and so forth, that kind of models. We also have something called a time series model, which is a form of modeling that takes into account how data points will behave if it is taken from a certain point in time. So it is taking into account the assumption that if data points are taken over like a season or a particular month or a year, there may be some kind of inherent bias or inherent pattern within that data set itself because it's taken from a particular point in time. Now, time series is quite complicated, so we're not going to go into that a whole lot today either. But what the main takeaway from this would be is there isn't really a correct model that you should be using when you are given a particular data set. And sometimes that can be very difficult to gauge or judge. So it is very much up to you to figure out what kind of models you want to use. And like I said, there is no one correct model that you should be using for one particular type of data set. If you have something to do with population growth or even analyzing traits within a population, whether that be something like alcoholism or crime rates against a particular neighborhood, you might want to try to use something along the lines of time series or regression, because you may not necessarily get a lot of clustering or probabilistic modeling going through that. But if you're, let's say, trying to classify something that might classify something in any kind of data set, more often than not, you should be able to use something along the lines of probabilistic modeling. And sometimes you could get away with using clustering models as well, depending on what kind of data types you have in your data set. Again, more often than not, you'll see an assortment of different models for one single data set. So it is better for you to be able to use multiple different types of models in order to have a better understanding of what your data is doing, and in order to better support your hypothesis or investigation as well. Finally, if we go to the slide about visualization, visualization comes in two main stages. One, you can visualize completely raw data, see what it's doing. And so this is happening right after pre-processing. This is before you've done any kind of modeling at all. So it's good practice to kind of have an understanding of what your data is doing, what it's looking like, what the distribution of your data is before you do any kind of modeling. Because sometimes when you're doing this visualization right after pre-processing, it will give you a bit of an understanding or a bit of a hint as to what kind of modeling you can potentially use, or what you need to do before you want to use a particular type of model. An example of this would be if you're using something like, if you want to use a model like naive Bayes theorem, that has an assumption that your data is normally distributed. Now, if you have data that isn't normally distributed, it gives you an understanding of what you need to do before you can actually use the model in the first place. The second stage of visualization is at the very end of modeling. So it is when you are trying to basically get a graph or a image, whether that be a scatter plot, anything of that kind. After you've done some kind of data wrangling or any kind of modeling, you get an image, and that basically shows you what your end result is. So you can go, when you're using something like Python, you can go from the very basics, such as a scatter plot or even a box plot. As you can see on the sides over here, the leftmost images, you'll be able to do something completely simple as that using very few lines of code in Python. You can even get a distribution through the histogram that we're seeing in the middle at the top. And you can even do something really complicated, such as if you want to figure out the accuracy of certain clustering groups and see what that's like against, if you have X number of clusters along the x-axis, see what the accuracy is if you're using that many clusters in a particular model. So that is given by the graph at the bottom middle. And the one at the very side is, on the right side, sorry, is a graph of PCA. So it is when you have data points that are of n dimensions, if you want to be able to get a better understanding of what that's doing, more often than not, you'd be using PCA, which can be used for dimension reduction. So if you have 2 PCA, basically means you're reducing it to 2 dimensions, and you can then create conclusions about what your data will look like, or even the distributions that are going on to make final decisions, or even gather conclusions about what you can potentially say about that kind of data. So, so far for this particular portion, do we have any questions about what we have covered so far? Cool. So what we'll probably do is we'll go to our Jupyter Notebook and do some of the exercises there and see how what we have been going through in this particular presentation, how that can actually be applied. Can everyone see my screen?
Yes.
Great. So when we have a particular data set that we want to use, we want to first be able to bring that into something like Jupyter Notebook in order to actually deal with the data in the first place. Now, there are multiple ways of reading data. We're going to go through 3 today. The first one is if you're importing data set from something like a library called sklearn. So if you're using Python, you'll have a lot of different libraries such as pandas, sklearn, numpy that will help you immensely when you're doing any kind of analytics. So sklearn has some default data sets that you can use. If you have something, you can use the keyword datasets and then load. So if I do something like datasets, whoops, dot, and then tab. Oh, maybe it doesn't work in this one. More often than not, if you use something like Jupyter Notebook, if you're using Anaconda or something, you'll be able to get a whole bunch of different commands that you can use once you press tab. So it will give you something like load iris or other data sets that sklearn already has within its library. So this is the default data set we're using. It's called the iris data set. It's quite common. A lot of different people use this when they're doing introductory data analysis. So we use a command like this, where this is my variable name, and we're loading onto the data set here. Now, what I want to do is I want to create a data frame, which is something that is within the pandas library. So we declare pandas as PD, your PD.dataframe, and then you insert the iris dataset right there. Now, the advantage of using a data frame is that it allows you to do a lot of different analytics tools just based on the data sets itself. What that means is that if I have some records or some rows that just don't have any data in them, like it's just empty rows, I can basically just go the data frame dot drop NA, and essentially it will automatically remove those rows, and I have a much cleaner data set to deal with. So I recommend, if you're doing any kind of pre-processing, to ideally use the pandas library, because it will make your pre-processing a lot easier in the long run. So this is our data set, and we can see that here. This is what we come up with. So before we do this, I'm just going to comment out these rows at the bottom. And we're going to see what the difference is first. When I just load the data set from sklearn, this is what we're getting. So you see you have your rows, you have your data, yes, but you also have column names, which is just 0, 1, 2, and 3. Now that isn't very helpful to us. We don't really know what that really means. So what you can do is you can rename your columns by having something like this, where you have your class, which is going to be added later on, just as a 4th row right there. And then you also have the column names that you're adding, right? So that can be anything up to you as you feel is applicable for your data set. It makes life a lot easier in terms of just getting a better understanding, or just explaining to yourself what your data means and what it's doing. So if we remember this, and if I just comment this one out one more time, and I run that, we see that we have our column names appear up, right? And we also have our class at the final row as well, which comes from this particular line of code. Does that make sense to everyone so far? Great. So if we go to our second option is reading a CSV file that's already on your computer. So that is what we did earlier. We just imported the CSV file right into our notebook right here. So what you need to make sure is if your file is located somewhere where your notebook isn't, make sure you're copying the entire path. And if not, you can just put in the name of the CSV and it will load it itself. It's not a very hard thing to do in terms of that. So what you do is I have something called iris_file, just so I can discern it from what we did earlier. Made a data frame out of that, have something called read_CSV, which will automatically read in my CSV file, and I can print that out like so. Now, what I did in addition to this is that through this data frame, I am able to create different attributes depending on what class I have. So if we have a look at class, we have something called iris setosa, we have something called iris virginica, and we also have something called iris versicolor. So if I want to be able to just see the data points of just those classes individually, I can declare a variable, like let's say for the class setosa, I will take something called the lock function. And what that does is that it will basically equate one of your columns to a title, like so, which is going to be one of your column names. Now, .lock makes life much easier, especially when it comes to slicing your data set, right? So if I have something, if I comment out this right here, if I have something like this and I just uncomment setosa right there and I run it, it will give me all the data points about setosa. Ideally, sorry, but I just do that one as well at the bottom. Great. Similarly, if you have it for the rest of these as well, you can get the individual data points just for those particular classes, if that makes sense to everyone. So I'm just going to comment those back again. And another advantage of using something like the lock function is that you can create slicing based on just the column name itself. So if I have something along the lines of iris_file.lock, and then the column sepal length, where I'm just basically adding the column name, I can get all the data point information that is specific to the column sepal length, and it's 150 records, so which means it has all the records that I need. Now, you can probably see that there is an advantage of using something like this, where you can use the column name directly versus using something like this, where you have to use the column number. Sure, it is easy, like both of them work, but just for the sake of understanding, I feel something like this would be a lot easier for you to figure out in terms of what your data is doing and where, especially if you have multiple different columns. If you have something like the IRIS dataset where it's only like 4 columns, you could probably get away with adding the column number itself. But if you have something like 13, 14 different columns, if you actually use the column name itself, it will make life a lot easier for you in order to be able to understand what is going on where. Does that make sense to everyone so far? Feel free to either comment or just have yourself unmuted if you'd like to say anything. Great. So apart from that, there's also option number 3, where you are using a library called Seaborn. So Seaborn is specific to using something when you're trying to visualize data. You'll have, you can use Seaborn as SNS. And what that does is you can just have the simple code sns.load_dataset iris, and it will automatically create your dataset into a data frame. So it makes this entire situation a lot more doable when you have something as simple as that. So these are the 3 different ways where you can load data and do any kind of pre-processing. Now, if we go on further, let's assume that we have done all the pre-processing needed. Also, I'd like to say the IRIS dataset is very much an ideal dataset. It's not a real-world dataset, so all the pre-processing is already done for this. All our records are good to go, and it's perfectly fine to use on its own. So, going by that, let's just visualize some of the raw data that we have initially. Here, what we are doing is we're creating a histogram of each of our attributes. So that is for each of the columns that we have, which is our sepal length, sepal width, petal length, and petal width. So more often than not, if you see something like a histogram or a scatter plot, it will give you an understanding of what your distribution actually is to begin with. So what we see from here, sepal length is not entirely normally distributed. It's kind of there, but not really. It has a lot of different peaks going on, and it dies down a little bit right there, has a bit of a bump. Sepal width, on the other hand, is largely normally distributed. You can see a nice bell going on there. Petal length, on the other hand, has 2 main groupings. You have a grouping over here, which is between 1 to 2, and you have something around 2.8 to just less than 7 right here, which is normally distributed. And then finally, you have petal width, where it's basically all over the place. There isn't really much of a pattern to that kind of attribute. So if you do something like this at the very beginning, right after pre-processing, it will give you some kind of understanding of what you can do with your data and what kind of conclusion you can come up with just raw data on its own. Sometimes what you can do is make a discussion about what is the distinction between what happens with raw data and what you're doing right after you have modeled it, just to see what the differences are and how different kinds of pre-processing techniques will help you with getting a better data set in general. Hopefully that made sense to everyone. From there, today we are going to be implementing a probabilistic model, which is the naive Bayes theorem, which I mentioned earlier. Now, this model takes the assumption that your entire data set is normally distributed. Now, we can see that this is not necessarily the case here, but if you are able to get certain bin sizes, you can probably make this data set normally distributed. So we're not going to go into a lot of detail with that today. But if you have a model like this, when you're using the naive Bayes model, first you want to see what your features are, or what your attributes are. So these are everything that is not your classifier or what your class is. So when it comes to feature names, in this case, we have the attribute sepal length, sepal width, petal length, and petal width. When it comes to our classifier, which is this line right here, that will be your setosa, versicolor, and virginica. So that is what we saw earlier over here. So this line species or class is our classifier. Now, there are two main things that we can see from here, is that classifiers can be either named as numbers, like you see in this particular data set right here, or if you see down the bottom in this particular data set, you can see that classifiers can also be named with like words themselves. So it's up to you how you want to deal with that kind of data, and different models will be able to deal with that in different ways. So if we go back down, we can see that in classifier, if we are trying to do any kind of modeling, in this particular one, what we are trying to figure out is what is the likelihood that a particular record that we insert into this particular model will give us a certain class, and what is the probability that that particular record will be each of our classes, setosa, versicolor, or virginica. And at the bottom over here, we also get an accuracy measurement on how accurate our data is. So sometimes that can be quite useful to you, just so you can understand, if you're having multiple different kinds of models that you're using, which particular model is a better fit for your data. If you have something like, if you're using another probabilistic model, let's say, and you get an accuracy that is less than this particular model, it will give you an indication that, okay, I should use the model with the higher accuracy so I can get a better understanding of what is actually going on with my data, because it takes into account more things in a much more accurate manner, if that makes sense. So one really great thing about Python is that a lot of your modeling is already in libraries themselves. So it's not like you need to actually code how the Bayes theorem actually works. I mean, you can, but ideally you wouldn't want to. So if you have something like an import statement, like so, we have sklearn.naive Bayes from this particular library, you can just train your data set accordingly, where we're taking our training set to be about 67% and our testing set to be about 33% of the data set. And you run this particular line of code, it will basically do the entire computation for you, right? And from there, you can get your accuracy measurement. If you want to get an understanding of what this prediction actually is, so let's say ypred, so see what happens when you're actually predicting your testing set, which is going to be about 33% of data. Ypred just means it's the prediction, or like the class values you have. If I just uncomment that particular bit, what you get is a whole bunch of different numbers here, right? And each of those can be an account of what class it's in. So if you see 0, that means it's a classifier setosa. If you see 1, it's a versicolor. And if you see virginica, if you see 2, sorry, it's gonna be virginica. So in this case, what it means, if I have randomly selected 33% of my data set, this is going to be the classifications that I get for that randomly chosen test set. One thing that we need to keep in mind is when we're doing any kind of classification in terms of this, random state is actually quite important. If I have random state equals to 1, what it means is that I am selecting the same testing set every single time. So that means this particular bit, our array, is going to be identical every single time we run this code. If I get rid of it, however, and I run it, I get this as my classification. However, if I run it again, I get something completely different. So random state, if you want to see how your data set is behaving just for one particular set of test data, I'd say random state equals to 0 is something quite useful and handy. And that will also give a prediction at the very end and your accuracy. Does that make sense to everyone so far? Great. So that is what you want to do if you have something you're going from raw data all the way ultimately to your modeling, but you might not necessarily be able to model what your naive Bayes theorem looks like, because at the end of the day, it's a probabilistic model. So more often than not, you'll get something along the lines of accuracy or even just like an array like this. But if you want to go something from visualizing at the very beginning to visualizing at the very end, let's take the K-means model, which is going to be our clustering model. If we use our exact data set one more time, where we have taken features to be defined as these columns right here from sepal length all the way to petal length, and then we create a data frame using just the features, right? You can make a data set K, which is basically everything that's in your data set minus the classifier. And you don't really need to understand this bit of code right here, but what it essentially does is that for the number of clusters that you have down the bottom, it will give you what is your error rate for that particular clustering. So what you want to make sure is that the less error there is, hang on, let me rephrase this. You want to have the largest cluster you can get with the least amount of error to it. So in this case, we have a bit of a kink right at 3, where we have a pretty low error and a pretty distinct clustering that comes at cluster number 3. So what that means is that I can get 3 good clusters, or 3 is my optimal number of clusters that I can make out of this particular data set. So this is our initial pre-processing bit of visualization. If we go to the end and we do a little bit more coding, you can find this particular bit of code right in this URL right here, which is going to be the documentation for sklearn. You can get this particular plot right here, which kind of gives you an indication of if I do 3 clusters, what does my data actually look like when I model it using K-means? So you can see that there is this particular region right here, gives you all the points for CISSA. This particular region right here gives you the points for versicolor, and this entire region right here gives you the points for Virginica. So if I got a test data point and I put it into my classifier, sorry, if I put it into my model, and depending on where it falls on any of these regions, it will be able to tell me that, okay, this particular data point will fall in this class because of where it is in these regions. Does that make sense to everyone? Cool. So from this, we can see that Python is a very useful tool when it comes to any kind of visualization or data processing, whether that be pre-processing, modeling, or at the end of the day, something like this where you want to visualize your data. One takeaway that I would like to give everyone is that when you're doing something like this, documentation is going to be your best friend, essentially. So we don't always know what kind of thing we want to do. We don't always want to be able to code it. More often than not, you'll find that something is already in the documentation that does a lot of the complicated stuff for you. So if you have a look at the pandas documentation, which is what we used initially for pre-processing, if you have a look at sklearn, which will have a lot of your modeling stuff, if you have a look at Seaborn, which is going to be a lot of the stuff on visualization, sklearn also has a lot of visualization stuff. So feel free to have a search on any of those particular libraries, see what the documentation gives you, see if it's actually doing what you need to do. Additionally, it will also give you the different parameters that you need in order for that particular thing to work. So you can make it as nuanced or as general as you need it to be. So something like this, where we were doing the train test split, I don't necessarily need to have random state in there. But if I do, it makes my life a lot easier when it comes to classifying just one particular set of testing data. So that is essentially it from me on what we can do using data analytics just as a presentation, and also some of our visualization techniques. So if we have any questions, I am more than happy to take them.